So today we want to talk about pipelining. Yes, question. Yes. So the question is about up to what lecture going to be covered in the quiz. Yeah, up to Wednesday, up to Thursday, and then next week actually I'm going to have like a review session. So I mean, we're not going to introduce new content, but we're going to just have a review session of things that we learned up to this point. But I'm going to have a separate post on CampusFire explaining exactly the lecture numbers, the procedure for the exam, and all that. So wait for that. Any other questions? Your computer assignment 1 is out, right? As you've seen, there's not much time, so start early. Hopefully you have already started. If you haven't, do it today. It's very relevant to what we discussed last week, and it's also very relevant to the quiz. So make sure that you do it and do it carefully. And use go to the discussion sessions. The TAs and LAs are having extra slides talking about some tips and tricks that they use when they're designing they did the project. So make sure to go there and ask them questions. If you're also kind of lost and you don't know where to start, or there's a particular thing, like there is a bug in your code that you cannot debug and all that, go to the discussion sessions, share it with the LAs and TAs that will help you, okay? And then also feel free to post it on CampusFire, and then someone will help you with that as well. But use this kind of like, different tools that you have in order to get help, okay? And then as Tom was here, donate blood if you can. I highly encourage you to do so. Okay. Last week we talked about this design, the control flow, the controller and the data path design. We talked about the necessity of having a separate control unit and a data path unit, and we kind of explained different components in this system. What I want to reemphasize is your project should follow this design. So what we want you to do in your project is not coming up with an entirely new design or an ad hoc design. We want you to implement this design and being able to kind of like code this design. So think about each component as a separate function, and then the connection between these components as kind of inputs and outputs to those functions, okay? And then an important thing is that, as you will see in your homework, which is going to be posted sometime later this week, and in the project, there are certain instructions that we didn't cover. For example, LUI or shift right arithmetic and so on and so forth, like SB. We haven't discussed this. So if you want to, for example, run LUI in this design, you can't, because you don't have the support for it. So what you need to do first is being able to change this data path such that you can support these new instructions. Sometimes you just need to have a new wirings. For example, I don't know, you just add a new multiplexer somewhere, and that would be enough for supporting a particular instruction. Sometimes you may need to add additional components. Sometimes you need to add both data path and controller. So different instructions may require different things, so just keep that in mind. Yes? Yes, the question is, are we allowed to add control signals? Absolutely. Question is, can you make that more than 1 bit? Yes, you can make that more. So actually, like, for example, ALU up in this case is 2 bits. Yes, for the multiplexer, you can also have like 3 or 4 inputs. And in that case, make sure that the controller has multiple bits. Okay. The last thing we discussed last time was single cycle processor. We said that the design is slow. We talked about the critical path and how we actually find the critical path. And then we talked about the iron law of processor performance. And we said that the goal is reducing the CPU time. In order to reduce the CPU time, we need to reduce any or all of these things. We said that, okay, what we can do is adding, like, dividing the stages into multiple stage and creating this multi-cycle design, which what it does is reducing the cycle time, but unfortunately it increases the cycle per instruction. And we said that the solution for this design is using what we call pipeline. So let's see what that is, okay? So what we want to do is being able to reduce the cycle time, but at the same time, make the cycle per instruction at 1. So, or even better, as we're going to show you later when we are explaining superscalar processors, we're going to even reduce this to below 1, okay? And we said that instruction count is something that we're not going to mainly cover. This is what you do at the algorithm level and the compiler level. If you actually use better designs, you can reduce this. So our focus is basically these two parts here, okay? So how do we actually make our design better? We're going to introduce the notion of pipelining. So what is pipelining? I'm going to use the example that is used in the book to kind of like motivate the need. So think about, the process of washing your clothes, okay? So what you would do is think about it as kind of like 4 steps. You put it in the washer, you then take it out, put it in the dryer, then you fold your clothes, and then you hang it in the wardrobe or whatever, right? So these are the 4 steps. And then in a regular load, as one person in the home, for example, you do it one at a time, right? So you have to first wash it, then you have to put it in the dryer, you have to then fold them, and then you have to kind of like organize them. And if you, for example, think about this as a process that takes 1 hour each, if you start at 6 p.m., you finish at, sorry, if it takes 30 minutes each, if you start at 6 p.m., you finish at 8 p.m., okay? And then if you have multiple loads, let's say you live in a 4-bed, four person, in one apartment, then if each one of you wants to do this, then you have to kind of like, one person does it, the other person does it, and so on and so forth. So it takes this amount of time. But obviously, this is not what we are doing in real life, right? What we are doing in real life is we are actually having some overlap, right? So the moment that the washer is empty, the next person can start using the washer. The same thing with dryer, the same thing with folding, the same thing with organizing and hanging your clothes, right? So essentially, you can have this notion of overlapping between the resources in an environment. And this way, if you actually think about this, it's still one process. So the entire kind of wash cycle in this case, it still takes 2 hours for one person. But if you look at the total of 4 person, you will see that actually, because of the overlap, what used to be finishing at like 1:30 a.m. in the morning now finishes at 9:30 in the morning. So from the perspective of 4 instructions or 4 person at the same time, we managed to basically reduce the end-to-end time. How we did it, we basically increased the throughput, right? So we increase the latency per stage stays the same. The latency per load stays the same, but the end-to-end time for all 4 loads at the same time reduces significantly. Okay, so this is the idea of pipelining, basically. Okay, so remember I told you that, okay, essentially what we do is that we have 5 stages of the pipeline. Okay, so we add these 4 pipeline registers. We have our instruction memory, we have our register read, we have ALU, we have data memory, and we have write back. And again, to remind you of the design, this is how it looked like. So this is your instruction memory, this is your register read, this is your ALU read, this is your ALU operation, this is your memory, and this is your write back. So we show it this way. And now what we want to do is that we want to overlap these things the same way that we overlap our washing cycles and drying cycles, okay? So for example, we put the instruction 1 here, and then instruction 2 here, instruction 3 here. So how does it work? So think about this so this is a cycle by cycle behavior, okay? So this is cycle by cycle behavior. So this is cycle 1, this is cycle 2, this is cycle 3, this is cycle 4, 5, 6, and so on, okay? So in cycle 1, what I do is I bring the first instruction into my instruction fetch. Okay, so this would be my I1. Okay, then the next cycle comes, and this instruction advances to the next state. So I1 goes to register read. In a multi-cycle or single cycle design, we let I1 to finish before we let I2 to go inside our pipeline. And this will not give us the overlapping that we want. So what we do instead is that once I1 goes into the second stage, now this stage is empty, right? So this memory stage is empty. So now we can actually put I2 here. So if I look at the cycle 2, so if I look at this, oops. If I look at this, sorry about that. If I look at this diagonally, I'll see that essentially in cycle 2, my instruction 1 is in register read stage, and my instruction 2 is in the instruction memory stage. Then goes to cycle 3. This instruction can move to the ALU stage. So again, I1 will be here. Now this place is empty, so I can move I2 here. So I2 goes here. And now I can fetch a new instruction. So my I3 goes here. And this process continues, right? So this process continues. I1 go to the next stage, I2 advance. So and everything is kind of like becomes of this kind of lockstep, synchronized design that everybody just go to the next stage and the next stage and next. Yes. Yes, so here you're assuming that these instructions are independent. Soon we're going to run into problems of dependence between these instructions, and we're going to solve that problem. But yeah, think about this as basically, again, in this analogy, think about different groups of clothes that you want to wash. They have no dependency between each other, so you can actually, use them. You can use the washer for each one of them. Okay? All right, so how does this help? If I'm actually looking from the outside, that is the instruction that leaves the pipeline, if I manage to fill the pipeline and produce insert a new instruction at every clock cycle, then once the pipeline gets full, from the outside point of view, I'll see one instruction at a time that's coming out of my pipeline, right? In other words, by increasing the throughput, I managed to finish one instruction per cycle, right? As long as I have large enough programs that I can feed instruction, essentially the time it takes to finish instructions is equivalent of the number of cycles. In other words, I can finish one instruction per cycle. If I have 1,000 instruction, it takes 1,000 cycles to finish this, plus 5 cycles more to kind of fill the pipeline, but that's negligible compared to the total size of the program. Okay, so this way what I'm achieving from this is that I'm going to go back to 1 cycle per instruction thing that I had with single cycle, but just this notion of overlapping things with each other. But then the benefit is that now my cycle time significantly reduces. Look at this example here. Okay. Let's say I have 4 different types of instructions. I have load, store, R-type, and branch equal instruction. And let's say these are my 5 stages, okay? Look at them individually. You see that, for example, fetching takes 200 picoseconds, register read 100 picoseconds, ALU 200, memory 200, register write 100, okay? If I look at the total time, I see that, for example, for load, it takes 800, 700, 600, and so on and so forth. For single cycle, if you remember, for single cycle, I need to basically look at the single cycle. I need to basically look at the max of these total time, right? Maximum of these total time, which in this case is equal to 800 picosecond. So my cycle time is 800 picosecond. My CPI is 1, right? But if I look at the pipelining, right? So my CT would be the maximum time 800, CPI 1. if I look at the pipelining, I told you that the pipelining allows you to, clock these stages individually. So essentially, the cycle time now is the maximum of these stages. As you can see, the maximum is 200 picosecond. Okay? So my cycle time becomes 200 picosecond. So, 4 times smaller. But my CPI, if I manage to, feed the pipeline and then have one instruction at a time feeding into the pipeline, my CPI stays roughly the same. It's not going to be exactly one. It will be slightly over one, but very, very close to one. Okay? So if I actually use the iron law of the processor, the speed up that I'm going to get is going to be 4x more for pipeline, right? Basically, IC CPI CT, right? So it would be IC CPI CT over IC CPI CT. This one is for pipelining. And this one is for your regular single cycle, right? In both cases, the IC is the same, so you don't change the program, so the number of instructions does not change. Now we know that this number is 200 for pipelining. This number is 800. CPI is 1. CPI is 1. As a result, pipelining is 4 times faster than your single cycle, right? So essentially, in this particular example, you get 4 times faster the design of a single cycle. Does that make sense? Any questions? Yeah. No, we are just comparing single cycle with pipeline. We're not bringing the notion of multi-cycle. So multi-cycle would be still the CT would be 200, but CPI would have been 5, right? So you can actually compare it with this. Yes. You can use Amdahl's law here. Well, here you can assume that all the instructions you can feed it to the pipeline, so there is no non-parallel part, right? So Amdahl's law was when you have part that you can parallelize and part that you cannot parallelize. So in this case, for example, if there are instructions that for some reason you cannot feed it into the pipeline, then yes, the Amdahl's law would have been relevant. But soon you're going to see how we are actually making sure that we can always feed the pipeline with the instructions. Great. So this is the design that we are going after, right? So we have this, what we call a 5-stage pipeline. I told you last time why we are doing 5. The reason for 5 is that you want to have roughly the same time. So as you can see, for example, here, these numbers are roughly the same, and the important thing is the maximum of those. So you can, like, if you can break it down smaller, you have to make sure that everything is broken down smaller. Otherwise, if, for example, I make this 150, I'm not going to get any benefit because it's still the clock cycle is determined by the max, right? So if I want to break things down, I have to break all of them down even further. In modern processors, we have up to like 15 to 20 stages of the pipeline. But at some point, you're going to get what we call a diminishing returns, which means that adding more pipeline stages is not going to further reduce the cycle time because, again, you're going to limit it by the size that you can reduce. And actually increasing the number of pipeline registers has negative impact. For example, it increased significantly the power consumption. It also increased the area. So you don't want to add just a lot of registers without thinking about the performance. But if there is a meaningful performance gain, then by all means, you will add more pipeline stages. We go with 5 stages just because of the design that we have. Okay? All right, so now you might also wonder what happens to our controller. Now that we're kind of adding this stuff, what should we do with the controller? For the controller, we basically need to pass the control signals with the data. Remember I told you that, I1, for example, is here, and the next cycle I1 goes here, and then the next cycle I1 goes here. So when I say I1, I mean any data that are associated with that instruction. That data includes all the data path related data, as well as the controller data. So when we are passing things, we are passing controller things to the registers as well. Okay, so data and control data both are passed to the next stage and next stage and next stage. Okay, so essentially controller goes to these registers, and then in order to kind of distinguish them, so these controller signals are generated during the decode stage, right? Then it goes to the execution stage. Some of these control signals are going to be consumed in the execution stage, so I no longer need to pass it on. But the memory signals and write back signals needs to be passed on. The memory one going to be consumed, and then the write back one needs to go to the next stage. I'm actually going to show you the signals here so that now you will understand it a little bit better. Okay, so this is the same design that we had in the past, the exact same design that we described last time. But now what we are adding is that we are adding these control, this data path, this pipeline registers. So this one, I'm adding this one, I'm adding this one, and I'm adding this one, okay? And as you can see, now my wiring are different because now I need to account for the fact that I'm sending things to the next stage, okay? So how does it work? Essentially, the first thing that you realize is that I'm feeding this in things that I'm going to be used later into my pipeline registers, okay? So for example, if you can see here, this is your PC, right? So the PC goes to the pipeline registers, and then as you can see, it's being used here to create PC plus offset, right? So this is your PC plus offset. And then this PC plus offset goes into the distance stage and then goes back and goes back all the way here, okay? Then you have, RD, for example. So as you can see, this is your RD that goes here, goes all the way back to here. So this is the data that you're going to use to write to the registers, okay? Same story with, for example, this is the results from the ALU, right? So this is the results from ALU coming here, going back here, going back here. So generally, these are all same pipeline registers, but keep in mind about, pay attention to the timings. Which instruction is going to be used when is how you decide where to put each of these things. Yes. Good question. So the question is, if I have a branch instruction that is going to be taken, then what do I do with the next instruction? And that we're going to talk a lot about in the next week. This is called control flow hazard. So we need to fix that issue. So it's a big issue. For now, let's imagine everything PC plus 4. So I can feed the pipeline. Can I feed the pipeline is going to be a very big challenge that we're going to see a lot. So there's going to be a bunch of problems. I'm just simplifying it a lot here. Any other questions? And as you can see now, for example, look at this signal here, ALU source, right? So ALU source is still coming from the controller, but coming from the controller that was computed in the previous cycle. So when the instruction was in the decode stage, you create the controller signal, you feed that controller signal into the registers, and then you consume that control signal now here. So ALU source is now being read from the execution. It's no longer read directly from the controller because there is a different instruction here now, right? So it's kind of like you go back in time to use that information, right? So your instruction 1 first is here, then your instruction 1 goes here. That's when you create your control signals. You save it into your registers. now that the instruction 1 is here, you read it from here. You don't read it from here because now instruction 2 is here. Okay, so pay attention to the kind of where you connect these lines because now the timings are different. In the single cycle, things were transparent. You can connect anything from anywhere to anywhere because all the things were the same instruction. Now that you're doing the pipelining, you have to be very careful because each stage has a different instruction. Okay? Any questions? Yes. Yes, we're using registers to save both control and data. As you can see, for example, I'm also saving PC. I'm also saving RS1, RS2, immediates, the func3 and func7, RD. I'm saving all of that because if I don't save them, the next instruction, next cycle comes and it will overwrite things. So you always save them and you feed them together. So you say, okay, you guys are a group of instruction 1. You go all together to the next cycle, so the next, to the next stage of the pipeline. And then again, these things goes together in the next stage of the pipeline, and so on and so forth. Okay? Any other questions? Good. And as you can see, then we also have things like 0, for example, that in the past it was just going directly to this branch, but now we are doing the branch in the beginning of the memory stage. Later, when we are talking about branch prediction, we're gonna revisit this of like why we are doing this. But just keep in mind this kind of subtle things that you see in the processor pipeline. Okay. And also see that basically this is your RD that goes all the way and comes back from here. Okay, so this is the same signal, but as you can see, it basically goes through 4 stages of the pipeline and comes back because this is the write back stage RD versus decoding stage RD. These are not the same thing. Yes. Is pipeline 1 going to implement in your project? No, not this year. Mm-hmm. Your other question? And as I said, this is how we graphically show it, right? So add, load board, add I. So if I want to show it, it would be this way. So add comes to the instruction memory. Then in the second cycle, add is in the decode stage and load word comes into the instruction memory. Then in the third cycle, add goes to the ALU, load comes to the decode stage, and the other load, the new load, comes into the instruction memory. Next cycle, add goes to the data memory. Load board comes here. The other load boards comes here. The new add comes here. Add goes here. Load board. The new add. If I have more instructions, I would have add them here. I'm just showing you 4 of them. At this cycle, then add is finished. So add is kind of what we call retired from the pipeline. It's no longer there. So that means that now load word can goes to this stage, load word can goes to this stage, add comes here. And then again, load here is done. So it retires. The other load word comes here, add comes here. And then this one is retired. And then finally add comes here and add is retired, right? So this process takes this many cycles to run these 4 instructions. Yes. For few cycles, some of these things are empty. Yes, it takes a little bit of time to fill the pipeline. Yes. Mm-hmm. Yes. So for now, don't worry about the dependencies, but yeah, there will be some dependencies. Soon I'm going to talk about them. Yes. Yes. So are they buying the set? Yes. I mean, these are same set of registers. So you still have that 32 registers. You don't duplicate the registers with instructions. we have to make sure that it happens. Otherwise, we're going to have what we call a control flow hazard, data flow hazards. I'm going to talk about it too. Yeah. Make your own opcodes. Are you talking about the computer assignments? Yeah. Oh, okay. So the question is about the computer assignments and whether we are allowed to use your own opcode. No, use the opcodes that's in the response. Yeah. It's a pipeline design. Yeah, well, multi-cycle has a specific meaning, right? Multi-cycle means that one instruction takes multiple cycles to finish, and then I'm not allowed to use anything else in the system. Okay. So pipeline is kind of like an advanced version of a multi-cycle, which I can overlap things. Okay. So this is a pipeline design, which is, yeah, one instruction takes 5 cycles to finish. But the difference is, as one instruction is going through the pipeline stages, I feed the next instruction in as well. Okay. All right. Another thing to see here is the shades. Okay. Shade means that you are using that component. So, for example, as you can see, DM data memory is white because add instruction does not use it. Versus load word instruction, you see that I half shaded my memory because data memory is being used. Okay. Another thing is reading happens in writing happens at the beginning half. Okay. And reading happens in the second half. Okay. So in this case, when I'm reading reading from the memory, it happens here. When I'm when I'm writing it, I'm writing in the first half. When I'm reading it in the second half. This is a notion that we're gonna later see. It's called half cycle. Writing always happens in the first half cycle of a clock cycle. Reading happens in the second half of the clock cycle. The importance of this half cycle is that if I want to read and write from the same thing, as long as I write in the first half cycle and read in the second half cycle, I can do it within one cycle. Okay? Yes. So as you can see, for example, here, if I want to read the same, if I'm writing to a register, for example, X12, and if I wanted to read X12 in this cycle, I could. Because writes happens in the first half cycle, read happens in the second half cycle. So I can read and write in the same registers in the same cycle. Okay? All right. So now some of you already asked these questions, as in there are 2 problems that we're going to see. And we're going to talk about this for the rest of this lecture and the next lecture. And that is this always possible that I can feed things to my pipeline? Consider a scenario like this, right? So let's say I have add x5, x1, x2, and I have subtract x20, x5, x4. What you see here is that in this case, x5, x5 is your destination register, right? X5 is your destination register, is the register that you write the result to it, versus X5 here is one of the source registers, is one of the operands of the instruction. Okay, so if you actually look into the timeline for this particular case where X5 is the destination register, the write happens at the first half cycles of this cycle, cycle 5, right? But now if I put sub, you will see that in order to feed the pipeline, if sub comes exactly after add, the time that we need to read the register, this X5, is actually here. And this is cycle, if this is cycle 1 and this is cycle 2 and this is cycle 3 and this is cycle 4 and this is cycle 5, I need the updated value of x5 in cycle 3, but the updated value of x5 is produced in cycle 5. And one thing that we know, everybody knows, is that you can never go back in time, right? So you cannot produce things that hasn't been produced, okay? Another interesting thing is, so this is what we call a data hazard, which means that if I ignore this problem and just run this program as is, x5 will read an incorrect value, an unupdated value, an old value, right? Which results in a correctness issue, right? So you have a variable, your variable is supposed to be updated, and the next instruction should use the updated value of the variable, and you're not. And the important thing is that this is completely opaque and invisible to the programmer. The programmer writes these things without any knowledge that what sort of pipelining you are using, whether or not you're using pipelining, the timing of your pipeline, anything like that. It assumes that it can run things as long as you follow these instructions. This program should run correctly and produce the correct results. So this is the job of the hardware designer, the microarchitecture, to fix this issue. The programmer does not know anything about this problem and cannot fix this issue. Okay, so generally this is what we call a hazard. Essentially, hazard is a situation when, because of the pipelining, we create incorrect results, that we need a particular data or code that is not available in the correct time and is available in future times. Okay, there are 3 groups of hazards that you're going to see. There is what we call data hazard, there is what we call control hazard, and there is a structural hazards. Okay, we're going to talk about each one of them one by one. The majority of our time would be on data hazards and control hazards. Okay, so what is a data hazard? Data hazard happens when you need an operand, but your operand is not available. Why is not available? Because previous instruction, older instructions are writing to it. So for example, you need register x5, and there is a previous instruction that's still working on x5 and updating x5. If you read the value of x5 before the value is actually updated, you are running into data hazards. Okay, so what are the hazards that you're worried about? There are 4 groups of data hazards that you may need to pay attention to. The most obvious one is what we call a raw data hazard. This is called read after write. Okay, so the examples that I gave you was read after write. So I'm reading this register after writing it to it. Okay, so in other words, when you're writing to RD and you're using the RS and RS2 before RD is actually finished, that is, before this instruction reached to the write back stage, you want to read RS1 or RS2. Okay, this is what we call a raw data hazard, or read after write data hazard. Okay, there is also another possible. So first of all, how many cycles do you need? We need to wait for, like, how many instructions do we have raw data hazards for? So if I have this add instruction here, if I can delay this next instruction, how many cycles do I need to delay it until I no longer have the raw data hazard? 2, right? Why 2? Essentially, if I look at this, so if I have my add instruction, as I said, the add is generated here. So if I do sub right after it, it cannot work. If I wait another cycle and do another, like and or whatever, it's still not going to work. But after the 3rd cycle, it can work. The reason that it does work is because of the half cycle. Because I can write to x5 in the first half cycle of this cycle. So I write it here. And I read it in the second half cycle. Okay, so I need 2 cycles. Any instructions that are dependent to each other has to have a distance of 2. Otherwise, I'm going to run into data hazards. Okay, But later on, we're going to improve this using other techniques that I'm going to describe later. But for now, just keep in mind that I need to be able to have at least minimum distance of 2 cycles between any instructions that has raw data hazards. Does anyone have any questions of why this is 2 and not 3 or 4? Yes. Yes. So it's, someone asked this patterns of half cycle. This is like enforced in hardware, and the answer is yes. All you need to do is making sure that your write delay is less than half of a cycle, and your write is synchronized with the clock. That's how you do it. Okay. But of course, there might be designs that doesn't follow the half cycle. So it's not like half cycle is like a universal law or something. The design can be, you can design your hardware such that it has this property. Okay, so as I said, there are multiple hazards. In addition to raw data hazard, read after write, you have 3 other types of hazards as well. You have what we call write after write hazards. You have write after read hazards. And for the sake of completeness, you can also have read after read. Read after read obviously is not a hazard because you're just reading the same value over and over again. So the timing is not an issue, right? You can just read things. If you don't update it, you can read it anytime. So that's totally fine. But let's talk about write after write and write after read hazards as well. Okay, so what is a write after write hazard? This is what we call output dependency. An example of a write after write is something like this: sub x5, x1, x2, sub x1, x2, and then let's say I have an add instruction that also use x5, but this time like x3 and x4. It could be also x1, x2, doesn't matter. But what is happening is that I'm writing to the same register twice, okay? This is what we call write after write or output dependency. What you want to happen is that you want this finished after this, right? Because this is the program order. This is what the software designer, software engineer was intended to do. So you want to do that. Luckily, since we are now only focusing on in-order processors, things are naturally happening in order. So this is not going to be moved around. So I'm not going to have output dependency as a hazard. Always we are guaranteed, as long as we execute sub first and then do add next, things will be taken care of automatically because I'm just running them one by one, okay? Later on, when we are introducing the out of order execution, you will see that there might be a possibility that add happens before sub, and there we need to take care of this. So for now, this is not a problem in our in-order processors, okay? Second one is what we call write after read. This one is also not a dependency. This is actually indeed called false dependency. So examples is again sub x5, x1 and x2, and this one is add x2, x3 and x4. So as you can see, I'm reading x2 and writing to x2 afterwards. Okay. So again, as long as I'm doing this in order of the program, nothing bad happens. If I move the order and run this before this, then this will become a problem. And again, for in-order processor, this is not a problem. That's why we call it false dependence. Okay. So going back to our raw data to data hazard, the only thing that we care about is raw data hazards. The other hazard is not important in an in-order processor. In pipeline in-order processors, those things are not important. Later, you're going to see that those are important. Okay? So how do we solve raw data hazards? Any solutions? Okay, so you kind of detect that there is a hazard, and then what? You wait. So you wait 2 cycles and then execute the instruction. So you kind of like not advancing your pipeline and say that, okay, you wait until this instruction finishes and then you go. Okay? Any other? And then where do you do this? Do you do it in hardware or do you do it in software? Yeah.
Oh. I guess like wait for 8 of them. At least for some of
Yeah, you have to wait 2 cycles, right? So yeah.
Yeah.
So ALU and the write back needs to happen, and then you can go.
Yeah.
Yes. So you make a copy. Okay, so you make it. So the comment was you make a copy of the destination registers, and then and then you use it when you can. Okay, yeah. Okay, so you kind of like have two register files at the same time. Okay, yeah. So you lock the registers, but then what if you want to update something you need to kind of somehow remember those things, right? If you lock your register files, you pass it. Okay, yeah, you can pass it. Yes.
Maybe each register at the line over say ready.
Okay, so each register says that it's ready, but
maybe the core people like in the state of change for these registers.
yeah.
That one. Sending the law.
Yeah, maybe. Yeah. Okay. Any final comment? Yeah. Uh-huh. Uh-huh. Uh-huh.
Transfer the data from the
Yes. So if we don't necessarily need for the write to the register file to finish, you can maybe transfer it from the ALU. Yes. Okay. All right. So I'm gonna give you a quick break, and then once we are back, I'm gonna talk about what we do. Okay. So how do we solve the raw data hazard? In order to solve the data hazard, we do the very simple thing. What we call stall the process. We stop the processor from fetching new instructions and advancing new instructions until the instruction that is producing the results reach into the write back stage. Okay, how do we do that? Option number 1 is you can do that by using the compiler, right? So compiler can do the following. It can insert the filler instructions into the sequence of instruction such that if this instruction and this instruction are dependent to each other, in this particular case, X19 is RD here and X19 in RS here, then as long as there is 2 instruction in between them, then we are safe, right? So what are the instructions that we can put here? There are 2 options we can do, right? So if the compiler can actually move things around, right, and can bring useful instructions from below this instruction that has no dependency with this instruction, then we can actually we don't need to stop the processor at all, right? So we just move instructions around as long as they're independent from each other. I feed it into this kind of like open slots and empty slots, then we are good to go, right? So for example, here, if I had, I don't know, an instruction like XOR X20, I don't know, X5, X6, right? This is perfectly fine to put it there, right? If I put it there or if I put it here or put it here, it doesn't matter, right? No dependency between them. So as long as I can move instructions from below and move it up and there's no dependency, so there's no like additional problems introduced, then I'm good to go. And I need to find two of them, right? So this is one thing that can be done. Of course, there is a big challenge here, and that is now, first of all, the compilation becomes very complicated because now the compiler needs to basically, first of all, understand all of these kind of dependencies. And not only that, needs to go and find instructions and move it up, and also needs to check the dependency of those instructions with these instructions. There's a whole bunch of things that needs to be done there. Some compilers are capable of doing that, and in fact, some of them are actually doing that. But many compilers cannot do that. Okay, just keep that in mind. So what do we do instead? We transfer this responsibility of finding instructions and moving things around to hardware. So dynamically, we actually do this. Okay. So the second option that, I mean, this can be done both in hardware or in compiler is we don't necessarily bring instructions from the bottom and move it up, but rather we create some arbitrary instructions, some no-op instructions or NOP instructions that doesn't do anything. It's just filler instructions, okay? So what is an example of a filler instruction? Think about something like this. Add x0, 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 okay? I'm just adding nothing with nothing and write the results to nothing, okay? This doesn't have any meaningful functionality, but what I can do is that whenever I see dependency here, I insert this no operation instruction. This is, by the way, called no-op or NOP. Some ISAs have a specific no-op instruction. Some others are just like, this add 0, add 0, add 0. So I put those instructions in between, and then I move on with my life. Okay, yes. The question is, doesn't that defeat the purpose of speeding up? Yes, it does generate like delays, but assuming that this doesn't happen often, then you're good to go, right? So, but yeah, you can make it faster, and I'm going to show you how to make that faster. Yeah, ideally you want that to be 0, right? So you want to be able to do that. Yes. So question is, does this no-op thing does this hardware define or does it compiler define? It could be both. So the compiler can detect these things and insert these no-ops, but again, same challenges because the compilation now takes a little bit more time, but it's possible. Usually the design that we go after and usually it's being used is that the hardware insert this. So hardware insert this in the fly, as I'm going to show you in the next few slides. Okay. So this is usually what we call a no-op or a bubble. So also some people call it a bubble. So you insert the bubble into your kind of pipeline. Bubble means that you're doing nothing basically. Okay. So it's kind of look like this, right? So like I see that instruction, I insert some bubble, some no-op instructions, and then eventually I get to the instruction that I want. Okay. So how do I insert the bubble? In hardware. So let's, for example, imagine a sequence like this. I have add x19, x0, x1, sub x2, x19, and x3. So this is my data hazard, okay? And let's say after the sub, I also have a XOR instruction that has nothing to do with these other instructions, okay? So here's the timeline, right? So add goes here in the first cycle. So remember, again, this is your cycles, right? These are your cycles. So add goes here, and your sub comes here. So far, so good. Add goes here, sub again can come here, and your XOR comes here, okay? Now add goes here, and now is when we have the problem, right? Because what happens during this cycle is sub is reading something that is old because the actual value is generated here, right? So if we advance sub, then we're going to run into problems, right? So what hardware does is that it understands that this is a hazard. So we need what we call a hazard detection unit during our decode stage to understand that this is a hazard. Then the second thing that we need to do is that instead of advancing this sub to the next stage, I need to replace this sub with my bubble. So I need to have a dynamic mechanism that I have sub in my decode state, but what I'm passing to the next stage is not a sub, it's a bubble, okay? And the third thing that we need to do is that since that this stage is occupied, now XOR cannot advance, because if XOR advancing to the next stage, it's going to overwrite the sub instruction. I want to keep the sub instruction inside my decode stage and only let it go when this add instruction reach to this stage here. So when add is here, then it's safe to let the sub go, right? So now I need to what we call stalling the processor from advancing. So essentially, in the next cycle, XOR should stay within the same state. I cannot let XOR to move forward. I cannot let sub to move forward. Instead, I insert bubbles, okay? And as you can see, this bubble needs to also be inserted here. So I need to, in the next cycle, I also need to insert another bubble from the ALU stage to the memory stage. And I need to insert that bubble from memory stage to the write back stage. Okay, so there are three things I need to do just to recap, and then I'm going to answer questions. One is I need to first detect that a situation like this happening. This is what we're going to add using what we call a hazard detection unit. Second, I need to substitute my sub instruction with the bubble, and I need to advance this bubble to the rest of my pipeline. And the third thing is that I need to stop the fetch and decode from advancing. So there are three different things that happen. So questions? So question is why XOR cannot move forward? The XOR cannot move forward because the decode stage is already occupied by the sub instruction, okay? The reason that we can move the pipeline is that sub goes to the next state, and then you have an empty stage that you can move the things over, right? So think about the line. You are in a line. If the person in front of you take a step forward, you can take a step forward. If the person in front of you doesn't take a step forward, you have to stay, right? So the bubble, instead of the sub moving forward, the bubble move forward, sub stayed put in the decode stage. As a result, XOR, and as a matter of fact, all the other instructions, future instructions, they're all stopped. Yeah. So the question is, does this happen in other stages? So since you're only focusing on the raw data hazard happens when you're reading the registers. Reading registers happen in the decode stage. So this data hazard happens in the decode stage. Later on, when we have like things like branch instructions or misspeculations that we're going to talk about later, those things happens later, and you may need to also like do things there. But for now, it's the decode stage. Yeah. So the question is, why are we not putting the bubbles here? The answer is, if it's an offline phase at the compiler stage, you can do that, okay? But this is hardware, right? So the hardware does not know the future. So it sees the sub and say, oh, we have a problem. So we insert the bubble. So the bubble is generated in the fly. Question is bubble. So bubbles you can think about is as an add x0, x0, x0. So what happens is that what I'm doing here is that when I'm saying I'm inserting a bubble, I do what, imagine that here it was an add x0, x0, x0. What would you pass? You pass that, right? So the controller knows that this is the control signal for a bubble. I'm going to pass that. And then all the values zero. So I'm going to pass zeros all the way. So RD, RS1, RS2, func3, func7, everything zero. My control signal is also equivalent of an add instruction. I'm going to pass until the add reaches to the write back stage. You just let it go. Now you just let it go, right? So it's like a stop, sub, add reaches to the write back stage. Now you let go. Starts like, think about this, is that sub, now all of a sudden bubble. So kind of you would have passed sub to the next stage, right? So you had the control signal for the sub, you have RS1 for the sub, you have RS2 for the sub. You replace that with zeros. I'm going to show you the data path, you'll see it. But yeah, that's kind of like, take that out, replace it with zeros. So you inject the bubble inside your code. Mm-hmm. Can you repeat the first part of the question? So I think if I understand the question was, when do we know when to let the sub goes to normally, right? Like, when do we know that this problem is gone and then we can execute normally? Is that the question? So how do you make sure that the instruction stays on the one stage? You basically disable the write enable here. I'm going to show you the data path. You will see exactly how we are inserting. From just qualitatively, what you do is that you force the registers. You prevent the registers from being updated. That's what you do. With the write enable, you'll do that. Yeah. Yeah. So you don't. So the question is, when do we know we have a hazard? We know that we have a hazard when sub reaches to the decode stage. When sub reaches to the decode stage, we know we have a hazard. At runtime, yes. Everything is at runtime. So everything is in hardware. Yes. One final question. Yeah. So the question, every hardware knows what is their no op. So the question is, like, how do we know it's X0 and why is add X0, X0, X0? Is that your question? Yeah. So the hardware knows what is their bubble. So this is something that you hard code in the hardware. So as I said, some ISAs actually do have a specific no op. I think ARM actually has an instruction literally called no op, or maybe MIPS has it. I don't remember correctly. RISC-V doesn't have it. It understands the concept of no op, which is replaced by add X0, X0, X0. But it's hard coded in hardware. Actually, let me see if I have. Yeah, this is just how we insert the no ops. Okay. Let me show you yes. Okay, so this is how we are actually inserting these things. Okay. Remember I told you that they have a controller. I have a controller here. So here's what I'm introducing. Okay. I put a mux. And what I do is that whenever I decide that I have a hazard, and then by the way, I have a hazard detection unit that also in this stage, the hazard detection unit issue a controller signal that basically decide between the regular control signals or a zero. So zero means that everything will be passed as zeros to the next stage. So whenever we see that we need to insert a bubble, all we need to do is that making that control signal equal to 1. That means that I'm going to basically pass 0 all the way. Okay, this is how we insert zeros. The second question that someone asked, how do we prevent the registers from advancing? We are introducing these two new control signals called IFID write and PC write. These are write enabled for your registers. If they are 0, this value not going to get updated. This value is not going to get updated, which means that whatever instructions was here stays here. Whatever instruction was here stays here. Everything else moves forward. So you let the PCs, all these other registers to update. You pass zeros by inserting bubbles. So execution, memory, and write back continues normally. You just substitute your regular instructions with bubbles, but you don't let these two instructions, which in this case was XOR here and sub here, you don't let these two to advance. once your add instruction reaches to this stage, then you let these guys go. So you make this equal to 1, and you also make this equal to 1. That's how you can let these instructions go. So that's at that point, you just continue normally. Does that make sense? Yeah. Yes. So if you, the question is that what if you have 3 instructions, one after another that has dependencies? You can. You always first do the first 2 that are closest. You fix that. If the problem still exists, you continue doing stalling. So yeah, it might be like 5 instructions, one after another. You have to stall all the way, which is terrible for your performance. But you may do that. Yes. You might also have dependency between RS1 and RD and RS2 and RD of like, you can have all these mixtures, but technically all of them was the same procedure. Yeah. If you do it in software and hardware, how much slower would that be? It wouldn't be exactly, it would be exactly the same, right? So if I insert 2 no op instruction here, then in terms of timeline, it would be exactly the same. It's just the difference would be that the software needs to go through the entire execution of the program, detect all the possible dependencies, and insert this. So it would be a little bit slow to do this for a very complicated program. Yeah. So the question is, why wouldn't that inserting bubble basically override previous instructions? That's why we do x0, 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 right? So you let x0 go, it overrides x0, which is already 0. So the pipeline, right? So in the original pipeline, your pipeline should have been like, imagine that there wasn't any dependencies, right? So this would have been what happens, right? Your add goes here, your sub comes, your add goes here, your sub comes here, your XOR comes here. And now imagine that there wasn't any dependency. In the next cycle, what would have happened is add, sub, XOR, add, sub, XOR, right? This would have happened. Now what we are doing is that essentially we're saying that, oh, this is not sub, this is a bubble. This is also a bubble. This is also not XOR. This is a still sub. And this is in the next cycle will be a bubble, and so on and so on. Right? So I'm replacing what would be a sub with a bubble. So I'm basically for a few cycles, I'm not doing anything useful. That's what we are doing. We're not replacing anything useful. We're just doing something not useful. Yes. Yeah, so as I said, the option number 1 was that compiler can actually move its useful instructions from the bottom that are independent from these instructions and move it there. That's also an option. And that's possible, and some compilers does that. But again, it's not going to be easy all the time. But later, we're going to fix this issue altogether so that you're going to see why we're not going to issue bubble all the time. So we're going to have a better solution. Okay. All right, so to just kind of reviewing what we just said, stopping part of the processor called stalling. So when you heard the word stall, means that you're partially stopping the processor. But as you have seen, technically we're not stopping the entire processor, right? We are stalling the fetch and decode, but we let execution, memory, and write back to move forward because we want to at some point allow the add instruction reach to the write back. If we stall the entire processor, you're going to basically create a deadlock, right? Because the instruction stays in each state and you never advance. So you let execution, memory, and write back to move forward, but you let your fetch and decode to stall, okay? So just keep that in mind. And then since you let execution, memory, and write back to move forward, since you're stalling your sub, you're replacing your sub with this no op or bubble instructions, okay? And this is, as I said, how you implement it in hardware. I'm going to show you the rest of it once I'm introducing the other concept. So you're going to see the full picture, okay? All right, so now that you guys are asking these questions of, okay, that seems to be that if there are lots of dependency, I'm basically wasting a lot of cycles. So is there a better option? How do we actually kind of do this without stalling the processor? This is the idea of what we call forwarding, okay? Or sometimes people call it bypassing. So what is forwarding? Let's revisit the example that we had before. We had add x5, and we are using x5 as the source. So let's see actually when x5 is really generated. Remember I told you that essentially we need to wait here because we are writing to the register file here, and at this point it is safe to read it, right? But if you actually look into this add instruction, you will see that I'm reading x1 and x2 in this cycle. These are my source registers. I'm actually doing the add instruction here. So here at the end of this cycle, I actually have the updated value of x5, right? But I only write it to the register file 2 cycles later. So there is an opportunity here that if I somehow let this value to overwrite the value that I'm reading from the register. So at this point, I'm reading x5 and x4, but since x5 hasn't been updated, this is an old value. I don't like this value, right? But if I somehow allow this value to overwrite the value that I'm reading from the register file, then I'm good to go, right? I don't need to read it directly from the register file. I basically forward it from the output of the ALU to the input of my ALU. So I'm kind of like, using the value that I generated in the previous cycle to the next cycle, okay? And the same idea for if the instructions are 2 instructions, 1 cycle down. So again, so this problem is fixed by this forwarding. If I look at this x5 and x5 here, so as I said, this is the updated value of x5. It goes to the next cycle. Again, here I have the updated value of x5. I can forward this to here, and again, I'm going to have the updated value of x5, right? So essentially what I need to do is this register to register transfer, which either I transfer it from the ALU results to ALU source or from the memory to ALU source, okay? So this is how it looked like. Remember I had the ALU and I had RS1 and RS2 or RS2 and the immediates. I'm going to introduce these 2 new muxes, 1 mux here and 1 mux here. And the way I'm going to do this is that now you can see that it gets the original value that it was supposed to get. This is the value that I'm reading from register file 1 and from the register file. But in addition to that, I'm introducing this value that is coming from here. I'm also introducing the value that is coming from here. Okay. So these 2 values are the values that are basically coming from this stage, beginning of this stage, and beginning of this stage. Okay, these 2 values are essentially equivalent of what I'm showing you here. This is the updated value of x5. This is the updated value of x5. So what I need to do is that similar to hazard detection unit, I need what we call a forwarding unit that detects that there is a forwarding opportunity. And what it does is that issues this control signals. And this control signals basically says that, oh, discard this value and instead use the value that is coming from here or use the value that's coming from here. Okay? You had a question, someone had a question? Yeah. Yes, so as you can see, basically the input, so remember what is important is that what is the input to your ALU, right? If I didn't have this multiplexer, the input to your ALU would have been like this. your register, and then this would be your register file. So this is your register file, right? This is your pipeline register, and this is the input to ALU, right? So cycle after cycle, that's how you read it. Okay? So now but here's the problem, right? If I read an old value here, this old value will be passed through the pipeline and will be read here. Okay? So what I'm doing now is that I'm putting a multiplexer here. Okay? So I'm putting a multiplexer here, and I introduce a new value, and I pass this value to my ALU. Okay? Where is this value is coming from? This value is coming from either from this stage, from this register, or from this register. These are the registers that have the updated value of X5, because in the previous cycle, X5 was actually updated, as I have it here. Okay? So again, if you look at this timeline, if I look at this cycle here, actually, let me go back one. Yeah. So repeating this, in cycle number 2, you have X1 and X2. Okay? In cycle number 3, you have X1 here and X2 here, and you have your updated value of X5 here. So this is the correct value of X5. Okay? Here, I'm reading X1, I'm reading X5 and X4, but this is the old value of X4, because I haven't updated the register file yet. So if I just forward this, if I just move on with this value here, this will be wrong, right? Because this is the old value. But if I somehow reroute this number here, X5 here, and then insert it here, then I'm good to go. Right? So that's basically what happens here. So I'm basically saying that the value that is going to the ALU is not the value that I read from the register file, but it's replaced by the result of the ALU from the previous cycle. Yeah, you had a question. So depends on the timeline, right? So the question is, do we forward from memory or do we forward from ALU? If it's immediately after, you have to forward it from the memory. If it's 2 instructions down, then you forward it from the write back stage, because the timeline is just, the instruction also moves forward, right? Questions? Okay. So I introduce a new thing here. As you can see, it's a forwarding unit. Okay. The forwarding unit basically checks whether the destination registers and source registers of destination register of a previous instruction and the source registers of a new instructions match. If it does, it replaces the value read from the register file with the value that is computed by the ALU. Okay. So now I'm adding an additional problem to this sequence, and that is, can you always do the forwarding? Does forwarding always fix this problem? Yeah. Exactly. So if you have a load word, so what I said here, this timeline, I always say that, oh, your value is available here. Your value is only available here if this is an R-type instruction or I-type instruction. If this is a load word instruction, then your value is not available here. Your value is available here, which means that you cannot forward anything from here to here because that value is still not updated. You can only forward things from here to here. So if I have a load word instruction here and then a sub instruction here, forwarding not going to help. Let me actually give you a concrete example. So let's say I have a load word for the X2, and I have a sub X20, X5, X4. So as you can see here, X5 is a destination register, and sub is a source register. Since the value is not available here, I cannot forward anything here. okay? I can only forward things once I read from memory, okay? And then I can forward, but I need it at the beginning, right? So I need it at the beginning of this cycle, but I only have this value at the end of that cycle. So I cannot do the same, I cannot do the forwarding here. What I can do though is that I can forward from here to here. That's I can do. So what you would need to do for a load, this is by the way called load use data hazard. When you have the data from the load instruction immediately needs to be used, okay? For load use data hazard, you need to stall by one cycle so that this instruction gets here, and then from here you can forward it to your ALU operation, okay? So, so essentially it would look like something like this, that your load now, you have the correct value here, the value goes here, then you forward it to your ALU operation and you're good to go, okay? So you still do the forwarding for load use, but you still need to stall for one cycle. If you didn't forward, then you had to go back to the 2 cycle stalling that you had before. Okay? Yes. 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 So you still, so you cannot, you don't have the correct value here. You only have it at the end of the cycle, which means that you can forward it at the beginning of the next cycle. And then you can forward it here. If you didn't have forwarding, then you will have another no op here, and then you would read it from the register directly. So that would be 2 cycles of stall. Okay? So we do forwarding for load use data hazard, but we also need to stall for 1 cycle. And there is no solution for this. You cannot do anything. Make sense? Good. All right. So to just recap, I introduced you multiple concepts. First, I introduced the notion of pipelining and show you why pipelining helps us to increase the performance. I showed you what are the changes required in our data path and controller to support pipelining. Essentially, the idea is that each instruction, think about it as a block of data and controller, and you pass this along your instruction to the next cycle, okay? Then we saw 2 problems. Problem number 1 was what we call data hazards, when there was dependency between the source and destination of the instructions. How do we fix that? There are 2 solutions. Number 1 solution is that you can stall. You have this thing called hazard detection unit that basically sees that there is a dependency between source and destination and stall the processor. How do we stall the processor? We insert the bubbles and we stop the fetch and decode from advancing, okay? But stalling means that, I need to waste 2 cycles to fix the data hazard problem, right? I don't like that. I want to able to run the processor all the time. So I introduced the second concept called forwarding. Forwarding basically allows you for R-type and I-type data instructions, since the value is actually indeed generated during the ALU stage and not during the write-back stage, I can take the values generated by ALU and push it back into the source of the ALU. So I basically replace the value that I read from the register file with the values generated by the ALU itself. How did I do that? I insert the multiplexer. I had the forwarding unit and I insert the multiplexer that basically says that, okay, discard this, use this, right? And I can forward from 2 places. I can forward from the memory stage and I can forward from write back stage. The reason that I need both of them is that if there is 1 instruction distance between the dependency, then I forward from memory. If there are 2 instruction distance, then I forward from write back. Sometimes I need to forward from both, actually. If there is 1 dependency here and 1 dependency there, I forward both of them, okay? Then the last thing is that unfortunately this only works if the value is available at the end of the ALU stage. And this is good for R-type and I-type instructions. For load board, this is not going to work. Why? Because load board data is available at the end of the memory stage, okay? So what do I do then? I need to go back to the stalling. So I stall one cycle. Now the value is available in the write back stage. Now I can forward it to my ALU. Okay, so I do a combination of forwarding and stalling for load use. So without forwarding, I would have waited 2 cycles for the load use to be resolved. Okay? Yes.
Can you explain the
Yeah.
how the stall and then
Yeah. So load word, as you can see, I have a load word and I want to use X5. The value of load word is available here, but this instruction reads the old value of X5 and passing the old value of X5 here. I cannot forward because the forwarding needs to happen at this moment in time, but the value is available at this moment in time. So one cycle is stalled for sure. Okay, now the value goes here, and if somehow I can forward from here to ALU, then I'm good to go, right? So this is how I do it. So I stall one cycle, I insert a no op, a bubble, then I'm forwarding from here to here, and I'm good to go. Okay? Good? Great. So what's the logic for detecting forwarding? This would be the logic, right? So essentially the logic says that if you have an instruction in the execution mem stage or in the memory write back stage, that the RD of that instruction is similar to either RS1 or RS2, then you would need to forward. And by the way, you make an additional check that this is even actually RD is going to be written. Because, for example, imagine that you're not actually writing to the RD. For example, this is a store instruction. For a store instruction, you're not going to have raw data hazard anyway. So you don't need to, you don't need to forward. Okay, so you forward only if either RD is equal to RS1 or RD is equal to RS2 of this is the old instruction, this is the new instruction. And you're writing to RD, right? So this is the second thing that you're checking. So in that case, you're forwarding from memory stage to the ALU execution stage. Similar thing from the write back stage. So similar idea. If the RD is equal to RS1 or RD is equal to RS2, and in fact you're writing to that registers, then you do the forward. And as I said, these are independent from each other. So you can forward both from the execution and write back at the same time. Okay? So these are the things that I'm showing, and this is actually the conditions. Now you can actually follow along. What are these conditions? This is the forwarding unit. I'm introducing 2 control signals to the forwarding unit. Okay? And then for load use, you basically check that RD and RS1, RS2, and you also check the mem read. Okay? So you check both of these, and then you do. But since you need to also stall, you have to basically check it during the decode stage. So for forwarding, you check the execution stage with memory or write back. For load use, you check the decode because you need to stall for 1 cycle first and then do the forwarding. So that's why you actually check it during the decode stage. So just keep that in mind, that there is a difference between the criteria, because this is basically the criteria for stalling, not forwarding. So you first stall and then forward. Okay? So this is the full picture with the hazard detection unit and your forwarding unit. The inserting the bubbles and then adding these kind of like, registers to stop the advancing. And this is your forwarding logic. Okay? Take a look at this, try to digest this, and feel free to ask any questions if you have one. Before I let you go, there are 2 other type of hazards. One is called structural hazard. Structural hazard happens when a unit is busy. Okay? So for example, let's say you want to read 3 register sources and you only have 2 ports. In that case, you cannot read all 3 at the same time. You need to stall and then you need to read the next one. In our design, this won't happen because we always make sure that everything is available. So you're not going to see structural hazard in our design, but If the design is very low power, for example, then you might see a structural hazard. But the bigger problem is when we're gonna have branches, and that's what we're gonna talk about next time, okay? So see you next time.
When will Homework 2 be released?
Probably sometime later this week,
This-
by like Friday.
Friday, and
Yeah.
then we will have until what date is the minute, roughly?
By Wednesday.
Oh, so, okay, so it'll be out on Friday, it'll be due on Wednesday,
Uh-huh,
just same day as the coding assignment.
yes, yeah, the times are tentative, I'm gonna announce it, exact times in
Oh, but the coding assignment has been finalized, like.
yes, the coding is
It's
finalized,
on Wednesday next week,
yes.
alright.
Professor.